quantum mechanics and...
One of the coolest and strangest parts
And today's deep dive
is tackling one of the most mind-boggling phenomenons in all of physics.
Quantum entanglement.
Even Einstein then called it.
Boot the action at a distance.
Yeah, he really did.
So how about this?
Okay, I'm listening.
You've got these two tiny particles of light, photons,
Right.
and they're entangled.
Okay.
Now you take a close look at one of them,
Mm-hmm.
and instantly, no matter how far apart they are, the other photon changes.
It changes in a very specific way, too.
Like they're connected by some invisible thread.
Totally defying the limits of space and time as we know them.
But come on, how is that even possible?
Well, first you need to understand this concept called superposition.
Oh yeah, I've heard of that.
Think of a coin spinning in the air, right?
Okay.
Until it lands, it's both heads and tails at the same time.
It's like it's in this blurry in-between state.
Exactly. And quantum particles are kind of like that spinning coin.
So they can exist in multiple states at once?
Precisely.
So it's not just that we don't know which state they're in, they're actually in both states simultaneously.
It's crazy.
What is crazy?
It's mind-blowing.
But how do we even create these entangled pairs? Like, where do they come from?
Well, there's this process called parametric down conversion.
Okay, I'm all ears.
It's like you're taking this high-energy photon,
Uh-huh.
and you're basically splitting its properties between two twin photons,
Wow.
creating this inseparable link between them.
So we've got these entangled pairs.
Yeah.
And they can be in multiple states at once.
Uh-huh.
And they're linked in this totally mysterious way.
Yep.
Yeah, I can see why Einstein called it spooky action.
Einstein really disliked this idea.
Did he ever?
Oh, yeah, he just absolutely hated it.
Well, I guess it does kind of mess with everything we thought we knew about the universe.
Yeah, it really does.
So what did he do about it?
He and some of his colleagues, they actually came up with this thing
Oh, yeah.
called the EPR paradox.
Right, the EPR paradox.
To try to argue that quantum mechanics, well, it must be missing something.
Like, there must be some simpler explanation.
Exactly.
He just couldn't accept that the universe was that strange.
They thought there's got to be some hidden variables.
Hidden variable.
Some secret instructions inside the particles that we just haven't figured out yet.
That predetermined the outcome.
You got it.
So Einstein thought there had to be a more straightforward, less spooky explanation.
Well, he really wanted there to be one.
But then Bell's theorem came along, right?
You know,
And it blew that whole idea out of the water.
it really did.
It actually gave us a way to test if those hidden variables even existed.
And what did the experiments show?
Surprise, surprise, Einstein's intuition was wrong.
This time, anyway.
Entanglement really is as bizarre and counterintuitive as it seems.
Totally.
So the universe is even weirder than Einstein imagined.
You're weirder.
That means we can't totally predict what's going to happen in the quantum world.
It's not like classical physics at all.
No determinism here.
It's all about probabilities and possibilities.
So this really changes how we understand reality, doesn't it?
I think it changes everything.
Absolutely.
And what's really exciting
What's that?
is that this weirdness of entanglement opens the door to some incredible applications.
Okay, so we know entanglement is real, stranger than fiction.
Right.
But can we actually do anything with it?
Oh, absolutely.
Wait, what?
You want to talk about mind-blowing possibilities?
Yeah.
Let's talk about quantum teleportation.
Wait, like Star Trek teleportation?
Okay, not quite like that. We're not beaming people up.
Right.
But we're talking about teleporting a quantum state.
A quantum state, okay.
Imagine you have a qubit, like a quantum bit of information,
Yeah.
and you want to send its exact state to someone far away.
Uh-huh.
Entanglement makes it possible to transfer that state
Right.
without physically moving the qubit itself.
Hold on.
What?
Are we talking faster than the speed of light here?
No, not quite.
Okay, because that's not possible, right?
It's not.
That would break all the rules.
It would.
So how does this teleportation thing actually work?
It's a bit of a trick using entanglement.
I knew it.
You start with two entangled particles,
Okay.
one with you and one with the person you want to send the information to.
All right.
Then you do a special measurement on your qubit and your half of the entangled pair.
Okay, I'm following so far.
And depending on the result of that measurement,
Uh-huh.
you send regular information, just ordinary bits, to the other person.
And then what?
They can use that information,
Yeah.
along with their half of the entangled pair,
Mm-hmm.
to recreate the exact state of your original qubit.
Whoa, so it's like the information is somehow transmitted through that entanglement link.
Exactly.
But wait a minute.
Yeah.
What happens to the original qubit?
Good question.
Is it like copied?
Nope, it's destroyed.
So the state is transferred, not copied.
Exactly.
This is wild.
And has some mind-blowing implications, especially for future technologies.
Like what?
Quantum computers, quantum networks.
Okay, I'm starting to see where this is going.
It's a whole new world.
So this is where entanglement gets really practical.
It gets practical and spooky.
What else can we do with it?
How about unbreakable encryption?
Unbreakable, now we're talking.
Imagine you and a friend want to share a secret message.
Uh-huh.
If you each have a photon from an entangled pair,
Okay.
You can use them to create a secret key.
And that key is impossible to intercept.
Exactly. It's totally secure.
This is starting to sound like science fiction.
I know, right?
But it's real, right? This is actually something scientists are working on.
It's as real as entanglement itself.
So what do they call this?
It's called quantum key distribution, or QKD.
QKD.
And it's already being developed by companies all over the world.
Wow.
It's like having an alarm system built right into your communication.
What do you mean?
If anyone tries to eavesdrop on your message,
Yeah.
the act of eavesdropping will disturb the entanglement.
So it's like it sets off an alarm,
It does.
alerting you to the intrusion.
You got it.
So in the future, things like online banking and private messages
All kinds of sensitive information.
could be protected by the laws of quantum mechanics?
That's the idea.
Incredible.
I told you it gets practical.
You weren't kidding.
And that's not all.
Really? What else?
There's more.
Give me more.
How about quantum computing?
Quantum computers, I've heard so much about them.
They're kind of a big deal.
But I still don't really get how they work.
Well, they're based on this idea of using qubits,
Qubits, right?
which can be both 0 and 1 at the same time.
Because of that superposition thing.
Exactly.
So instead of bits, which are either 0 or 1,
Like in a regular computer?
we have these qubits that are in this blurry, both at once state.
You got it.
And how does entanglement fit into all of this?
Well, by entangling multiple qubits together,
Uh-huh.
we can create these incredibly complex relationships between them.
And what does that allow us to do?
It lets quantum computers explore many different possibilities simultaneously.
So they're not limited to just one path at a time, like a regular computer.
Exactly.
They're kind of exploring all paths at the same time.
Which can lead to massive speedups for certain types of calculations.
Speed-ups like, how much faster are we talking?
For some problems,
Yeah.
a quantum computer could find a solution in minutes,
Really?
when it would take a regular computer billions of years.
Billions of years.
No joke.
This is blowing my mind.
I know, right?
So what kinds of things could we do with this kind of computing power?
Think about it. Designing new medicines, creating new materials, revolutionizing artificial intelligence.
I mean, that would change everything.
Pretty much.
But are we even close to having quantum computers that can do all of that?
We're getting there.
Really?
It's still early days.
So we're not quite at the Star Trek level yet.
Not quite.
But it's only a matter of time.
Yeah, I think so.
So we've gone from spooky action at a distance
To unbreakable encryption.
to world-changing computers.
And we're just getting started.
We've only just scratched the surface of entanglement, haven't we?
You're absolutely right.
There's so much more to explore.
So much more.
But before we move on to the really big picture stuff,
Yeah.
are there any other important concepts we need to understand about how entanglement works?
Well, in the real world,
Mm-hmm.
these entangled systems aren't perfectly isolated.
Right, things get messy.
They bump into other particles, interact with their environment.
It's not all neat and tidy like in a textbook.
Exactly.
So how do we deal with that?
That's where mixed states come in.
Mixed states.
Unlike the pristine pure states we've been talking about,
Uh-huh.
mixed states are more realistic.
Okay, so they take into account all the messiness of the real world.
They do.
Can you give me an example?
Sure. Imagine you've got your beautiful entangled pair of photons,
Okay.
but one of them bumps into an air molecule.
Uh-oh.
Suddenly, things aren't so simple anymore.
Right, the entanglement gets disrupted.
Exactly.
So how do we describe entanglement when it's not so pristine?
We use something called density matrices.
Density matrices.
They sound complicated,
Yeah, a little bit.
but the main idea is that they give us a way to describe entanglement,
Uh-huh.
even when our system is interacting with the environment.
So it's like a more robust way of dealing with entanglement.
Exactly.
That can handle the messiness of the real world.
You've got it.
And is there a way to actually measure how much entanglement is there in these mixed states?
There is.
How do we do that?
We use something called entanglement entropy.
Entanglement entropy.
It's a handy tool.
So is that like a thermometer for entanglement?
You could say that.
The more entangled the systems, the higher the reading.
That's the idea.
So it helps us track how entanglement changes over time.
Or how it's affected by different interactions.
This is getting pretty deep.
We're going deeper down the rabbit hole.
Already, are you?
Absolutely.
Let's do it.
Let's zoom out and see how this all plays into our understanding of the universe.
I am strapped in and ready for liftoff.
Buckle up, it's going to be a wild ride.
We've talked about how entanglement is weird
Super weird.
and how it defies our everyday intuition.
It really does.
But how does it affect our understanding of the universe on a grand scale?
Well, here's where things get really mind-blowing.
I'm ready.
Entanglement might be more than just a curious phenomenon.
What are you saying?
It might be one of the fundamental ingredients in the recipe of the universe itself.
Whoa.
It might even play a role in the very fabric of space and time.
Okay, now we're really getting into mind-blowing territory.
Hold on tight.
I've heard about this idea that space and time might not be as fundamental as we think,
You've heard right.
but I've never quite understood it.
It's definitely a mind-bending concept.
And it comes from some pretty advanced physics, right?
Yeah, it's from a very advanced area of theoretical physics.
Okay, so break it down for me.
The basic idea is this. Space and time, the stage upon which the cosmic drama unfolds,
Yeah.
they might actually emerge from the entanglement of quantum bits of information.
So instead of think of space and time as pre-existing entities,
Right.
we could imagine them as arising from how these quantum bits are entangled.
You got it.
So the fabric of space-time is like this tapestry woven together by the threads of entanglement.
That's a beautiful way to put it.
And there's even a formula that connects entanglement and geometry.
Yep, the Ryu-Takayanagi formula.
Ryu-Takayanagi.
It relates the amount of entanglement in a region of space to the geometry of a higher dimensional space.
Wait, higher dimensions?
We're going there.
Are we talking string theory and all that stuff?
It's all connected.
So entanglement could be the key to understanding some of the biggest mysteries in physics.
I think so.
This is getting heavy.
Hold on tight, we're just getting started. Welcome back to our deep dive into entanglement.
So before we zoom out to the universe, there's one more piece of the puzzle we need to explore.
Okay, what's up?
In the real world, these entangled systems,
Right.
they aren't perfectly isolated.
That's true.
They bump into other particles, interact with their environment, things get messy.
It's not a perfect world out there.
No, it's not.
It's definitely not a textbook scenario.
So how do we deal with that messiness?
Well, that's where the concept of mixed states comes in,
Mixed states.
as opposed to the pure states we've been talking about.
Okay, so pure states are like the idealized version.
Exactly.
And mixed states are more realistic.
More like what we actually see in experiments.
Can you give me an example?
Sure, imagine you've got your beautifully entangled pair of photons,
Okay, picture perfect entanglement.
but then one of them bumps into an air molecule.
Uh-oh, trouble in paradise.
Suddenly, things aren't so simple anymore.
Yeah, the entanglement gets all messed up.
It gets disrupted.
So how do we even describe entanglement when it's not so pristine?
We use something called density matrices.
Density matrices, all right, that sounds a bit complicated.
I know they have a kind of intimidating name.
Is this where I need a PhD in physics to follow along?
Not at all.
Okay, good.
The main takeaway here is that density matrices give us a way to describe entanglement,
Okay.
even when our system is interacting with the environment.
So it's a more robust way of thinking about entanglement
You could say that.
that can handle the messiness of the real world.
Exactly.
And there's got to be a way to actually measure how much entanglement is there in these mixed states, right?
There is.
I was hoping you'd say that.
What we use is something called entanglement entropy.
Entanglement entropy.
It's a really useful tool.
So it's like a thermometer for entanglement.
Yeah, I like that analogy.
The more entangled the systems are.
The higher the entanglement entropy.
I got it.
And just like a thermometer, it helps us track how entanglement changes.
Like over time or how it's affected by different interactions?
Precisely.
This is fascinating stuff, but I'm ready to zoom out a bit.
Okay, you want the big picture.
I want the cosmic perspective.
I like your style.
We've talked about how entanglement is weird,
It's definitely weird.
defies our everyday intuition.
Absolutely.
But how does it affect our understanding of the universe?
On a grand scale.
Yeah, on a grand scale.
Well, it turns out that entanglement,
Yeah.
it might be more than just a curious phenomenon.
Okay, I'm intrigued. Tell me more.
It might be one of the fundamental ingredients in the recipe of the universe itself.
Whoa, hold on. Are you saying that entanglement is like baked into the fabric of reality?
That's what some physicists believe.
This is getting mind-blowing.
And get this, it might even play a role in the very fabric of space and time.
Okay, now you're just messing with me.
I'm not, I promise.
I've heard about this idea that space and time might not be as fundamental as we think,
You've heard right?
but I've never quite grasped it. It's pretty out there.
It's definitely a mind-bending concept.
Can you try to explain it in a way that even I can understand?
I can try.
All right, let's hear it.
The basic idea
Yeah.
is that space and time, the stage upon which the cosmic drama unfolds,
Right, the backdrop of everything.
they might actually emerge
Emerge from what?
from the entanglement of quantum bits of information.
So instead of thinking of space and time as these pre-existing entities,
Yeah?
they're actually created by
Or at least they emerge from...
how these quantum bits are entangled.
Precisely.
So the fabric of space-time is like
It's like a tapestry.
woven together by the threads of entanglement.
Beautiful analogy.
And isn't there a formula that connects entanglement and geometry?
There is. It's called a Ryu-Takayanagi formula.
Ryu-Takayanagi. Okay, I'll try to remember that one.
It basically relates the amount of entanglement in a region of space
Okay.
to the geometry of a higher dimensional space.
Wait, higher dimensions? Now we're really going down the rabbit hole.
I told you it was a wild ride.
Are we talking string theory and all that stuff?
It's all connected.
This is incredible. So entanglement could be the key to understanding?
Some of the biggest mysteries in physics.
Black holes, the Big Bang, the whole shebang.
You got it.
This is heavy stuff.
But we're not done yet.
There's more.
Oh yeah, we're just getting started.
Welcome back to the deep dive. We've been on quite a journey,
We have.
exploring this mind-boggling world of quantum entanglement.
It's a strange world,
It is.
but it's full of possibilities.
That's right. And before we wrap things up,
Okay.
let's talk about how this seemingly bizarre phenomenon could reshape the world.
It's not just theory anymore.
So what are some of the potential applications of entanglement that could actually impact our everyday lives?
Well, one of the most exciting areas is quantum computing.
Quantum computing, yeah, we touched on that earlier.
We did.
But to be honest, my brain was still trying to wrap itself around vacuum entanglement at that point.
It's a lot to take in.
So can you remind us how entanglement makes these quantum computers so powerful?
Sure. Remember how regular computers use bits?
Which can be either 0 or 1.
Exactly.
But quantum computers use qubits.
Which can be in a superposition of both states simultaneously.
Right, like that spinning coin.
That's the one.
That's both heads and tails until you stop it.
And here's where entanglement comes in.
Okay, I'm listening.
By entangling multiple qubits together,
Uh-huh.
we create this web of interconnectedness
Okay.
that allows them to explore many different possibilities at the same time,
So it's like having millions of computers
or even more.
working together in perfect harmony,
Yep.
each exploring a different path to find the solution.
Precisely.
That's amazing.
It's what gives quantum computers their incredible speed advantage.
So what kind of problems could these quantum computers solve?
Problems that would take classical computers
Like our current computers?
billions of years, wow,
We could be talking about designing life-saving drugs,
at molecular level,
creating entirely new materials,
with amazing properties.
or revolutionizing artificial intelligence.
I mean, the possibilities are endless.
They really are. It sounds like quantum computers could truly change the world.
I think they will.
But I know there are still some pretty big challenges.
Oh yeah, for sure.
Before these quantum computers become a reality in our everyday lives.
Building and controlling large-scale quantum computers is incredibly difficult.
What are some of the biggest hurdles?
Well, one of the biggest is that these delicate, entangled states,
Right.
they're easily disrupted by their environment.
It's a noisy world out there.
It is.
And those quantum states are very fragile.
We call this decoherence.
Decoherence. It's like trying to build a house of cards in a hurricane.
That's a great analogy.
But despite the challenges,
Researchers are making amazing progress.
they are.
They're developing sophisticated error correction codes
Okay.
and new architectures that are more robust against decoherence.
So it's a race to see who can build the first truly fault-tolerant quantum computer
It is.
that can unlock all of this incredible potential.
It's a very exciting time to be in this field.
So maybe we won't have quantum computers on our desks next year.
Probably not next year.
But it seems like it's only a matter of time
I think so too.
before they start to revolutionize various fields.
I agree.
So what about other areas where entanglement could have a more immediate impact?
Well, there's quantum sensing and metrology.
Quantum sensing, I've heard of that.
It's another area where entanglement is showing a lot of promise.
So what can we do with quantum sensors?
You see, entangled particles,
Yeah.
they're incredibly sensitive to changes in their environment,
Really?
which makes them perfect for building ultra-precise sensors.
So we could use them to detect tiny changes in things like magnetic fields,
Exactly.
gravity,
Uh-huh.
even time itself?
That's the idea.
That's incredible. So what kind of applications are we talking about?
Imagine medical imaging devices
Okay.
that can detect diseases at their earliest stages,
That would be a game changer.
or navigation systems with unparalleled accuracy,
So we'd never get lost again.
or even the ability to detect gravitational waves,
With incredible sensitivity.
opening up new windows into the universe.
It seems like there's no limit to the potential applications of entanglement.
From the smallest scales to the largest.
But beyond these technological advancements,
Yeah,
entanglement also forces us to ask some pretty big philosophical questions.
it does.
Doesn't it?
It challenges our understanding of reality itself.
Yeah, it really does.
It suggests that the universe is far more interconnected
than we ever imagined.
than our everyday experience suggests,
If particles can be linked across vast distances,
sharing a destiny that transcends space and time.
it makes you wonder about the nature of separateness and connection.
It's a deep question,
It is.
and I don't think we have all the answers yet.
Maybe we're all connected in ways we're only beginning to understand,
Maybe the boundaries we perceive between objects.
are more illusory than real.
It's a mind-boggling concept.
It really is.
And as we continue to explore entanglement,
Uh-huh.
we may be forced to reevaluate our most basic assumptions about the universe
About reality itself.
and our place within it.
Well, we've reached the end of our deep dive into quantum entanglement.
It's been quite a journey.
And I have to say, it's been a truly mind-bending experience.
I agree.
We've covered so much ground.
From the fundamental
The
principles
mind-blowing
for
potential.
world-changing technologies.
And thought-provoking philosophical implications.
It's all connected.
It's a testament to the power of human curiosity.
And our desire to understand the universe.
And while we've explored a lot in this deep dive,
I think we've only scratched the surface of what entanglement has to offer.
I think you're right, and as we continue to unravel its mysteries,
Who knows what we'll discover?
we may find that entanglement is more than just a strange quantum phenomenon
It might just be the key.
to unlocking a deeper understanding of the very nature of reality itself.
It's an exciting time to be a physicist.
So, to everyone listening out there, stay curious, keep exploring.
And never stop asking questions.
Thanks for joining us on this deep dive into quantum entanglement.
It's been a pleasure.
Until next time, keep wondering, keep questioning.
And keep exploring the universe and all its mysteries.